Okay. Okay. Well, it's a great pleasure to welcome Alexia Chairman. He's going to join us virtually from Minnesota, I think Minneapolis, I think you said. And right. We're delighted to learn about universal deformations. So thank you very much for joining us, Alexia.
All right. Well, thank you so much for the invitation to talk. It's wonderful to join you, even if it's from very far away.
It's a shame that we are not able to get people visiting so much, but the advantage is that that we get to hear lots more seminars. So thanks again.
That's right. That's right. Yeah. So I'm going to try to tell you about universal deformations, and hopefully, but one of my goals is that you know what I mean by that by the end of the talk, because it's definitely not a standard term. The work I'll be telling you about was published last year, and it's with two graduate students here at Minnesota, Theo Jacobson and Maria Neusel, who are both absolutely fantastic. So if you ever see an application from them, please take it seriously. Let me just dive in, and also I should say, please do feel free to interrupt with questions. I've sort of assumed that the people know QFT stuff a little bit, at least, but feel free to ask any questions you want during the talk, and I'll slow down or speed up as necessary. Okay, so when we study quantum field theory, when we first begin the study of quantum field theory, one of the things that we try to do is we take some quantum field theory we understand, let's say one with an action S, and we deform it in various ways. So we add some perturbation and ask what happens. Sometimes we know how to understand the effects of such a perturbation, and sometimes we don't. Now, to understand which perturbations are actually important, and that is to understand the space of interesting quantum field theories and space of interesting parameters in any given quantum field theory, it's important to introduce the notion of a scaling dimension of an operator. So here the operator in question is this local operator O that you add to the action in a d-dimensional quantum field theory. And for me, d is the space-time dimension, since I'm from the high energy physics community. And the scaling dimension of an operator, if it's greater than the space-time dimension, then its effect is negligible at long distances. If you add it to the action at long distances, its effects just wash out. It's called an irrelevant operator. Whereas if its scaling dimension is less than the space-time dimension, then the deformation is called relevant. It's very important in the long distance limit, which is usually what we're actually interested in. And so it has very interesting effects. Now, I said earlier that sometimes we can understand what these kind of deformations do, that is to understand the dependence of a quantum field theory on some parameter, the parameter he being the coefficient of the deformation. But actually, that's very rare. We can almost never actually figure out what the effect of the deformation is exactly, especially when it's relevant. And perturbation theory, which is what we learn as graduate students, tends to be the best we can do. Sometimes there are fancier versions of it or less fancy versions, but basically we tend to just be doing perturbation theory. Okay, so let me now tell you the punchlines of the talk that I'll then try to justify as I go. So the first punchline is contrary to what I just said. There are interacting quantum field theories that don't have supersymmetry, that are not conformal field theories, they're not like particularly special, that have exactly solvable relevant deformations. So these are deformations by local operators which affect the long distance physics in a profound way, but you can understand the effects exactly without perturbation theory. There are examples of such theories in a variety of dimensions, but the simplest examples and possibly the most interesting ones so far are in two-dimensional quantum field theories. So quantum field theories that describe the physics of particles that can move along a line and also evolve in time. And in that context, the kind of deformations that I'll tell you about have some really entertaining implications for confinement, that is color confinement or quark confinement, which is of course a major topic in quantum field theory for many decades now. And apart from that, which I think is already kind of interesting, another fun consequence is that thinking through these kinds of things leads to rather peculiar examples of quantum field theories that violate something called the effective field theory naturalness principle. And to explain that will take some time. But if you've heard of the FT naturalness principle and its uses in particle physics, this last point might be of some interest. Okay, so those are the punchlines. Of course, at the moment, these are just claims. There's no reason for you to believe me on any of them. But I hope to convince you of at least some of them being true. Okay, so to understand these magical deformations that are exactly solvable, and these are the universal deformations of the title of the talk, I have to start in a kind of weird way. I have to start by telling you about the notion of symmetry in quantum field theory. So when we first meet symmetries in quantum field theory in most textbook treatments, we're told that a symmetry is the following thing. You take an action for a quantum field theory. The action is the integral of some Lagrangian. So here's a free scalar field theory with a massive scalar field. And an example of a symmetry is some transformation of the field, which leaves the action, or possibly the action together with the function integral measure, invariant. And when that happens, if it's a continuous symmetry, then you have a conserved current. And if you feel like it, you can define charge generators, conserved generators of the symmetry, which basically are exponentials with some parameter oops, of the charge associated with the symmetry. And the charge is the integral over all of space of the zeroth component of the conserved current. So all of that is fairly standard for anybody who's seen basic quantum field theory. Now, in a relativistic quantum field theory, I could always rotate over to Euclidean space. And then let's say space-time is not compact. So I don't have to put any boundary conditions on the fields explicitly, except that they fall off fast enough or something. And then space and time come on the same footing in Euclidean space. And what I could do, which may seem like a weird thing to do, but I could do it, is instead of thinking about the symmetry generators as being integrals with some parameter, sorry, exponentials of integrals over space of the conserved current, in Euclidean space, I could just, instead of integrating over all of space, I can just pick some closed three manifold, which could be space, but it doesn't have to be. It could be some other closed three manifold, and integrate the conserved current on that. And well, the conserved current, technically, if you think mathematically, it's actually a one form. So to integrate in a three manifold, here I'm assuming that I'm in 4 dimensions. You have to take the Hodge star of it, it's a negative 3 form, and then you can integrate it in 3 manifold. Anyway, this is just a fancy way of taking a new perspective on what a symmetry generator is that you could do in a relativistic field theory in Euclidean space. And then the fact that the current is conserved, which is in form language this equation right here, actually implies that if you deform the manifold in which you're integrating this conserved current a little bit, that there's no effect. So unless you cross some charged operator somewhere, these charge generators have only a topological dependence on the 3 manifold. So what this means is that if you have a quantum field theory with a U1 global symmetry, which is a very standard classic textbook thing to consider, that implies that that quantum field theory has codimension 1 topological operators. So for example, a 3 manifold, like closed 3 manifold M3 is codimension 1 in 4 dimensions. And I've assumed that I'm in 4 dimensions in writing this slide, but more generally, if I was in some other number of space-time dimensions, let's say I was in 1 + 1 dimension or something, then the manifold that I would be integrating in here would be a 1 manifold, 1-dimensional manifold. Okay, so this standard textbook perspective on symmetry immediately implies there are some weird operators in the quantum field theory which are topological, which are defined on some closed manifolds, which have codimension 1, and you could deform those manifolds without changing the properties of these funny operators. So this was emphasized, I don't know if it was discovered there, but it was certainly emphasized in 2014 in an important paper by Gayotto, Kapustin, Seiberg, and Willett, where they made the following observation. instead of thinking that a U1 symmetry is something that is defined the way I just said, which then implies the existence of these finite topological operators, you could turn your perspective around, and you could say that if your quantum field theory has some codimension 1 topological operators, or another way of saying it, d-1 dimensional topological operators. Topological operators defined on d-1 dimensional manifolds. That statement implies that it has a global symmetry, a standard global symmetry that acts on particles. Now, that's a very formal way of saying what a global symmetry is, but it's useful. The reason that it's useful is, first, everything you can normally do with symmetries, you can discuss in this language of topological operators. But what's really powerful is that you can generalize the notion of symmetry in a very productive way by taking this modern abstract perspective. So, for example, instead of considering d-1 dimensional topological operators, like I did on the a couple of slides ago, you could say, okay, what if I have a lower dimensional topological operator? So some operator, which is defined on some manifold. Okay, so it's not a local operator necessarily, but let's say it's defined on a d-1 minus p dimensional surface. Then, well, that defines some kind of symmetry, and it's called a p-form symmetry. And a p-form symmetry is a symmetry that acts on p-dimensional extended objects. So, for example, if p is 1, then what we were talking about are symmetries that act on basically one-dimensional extended objects. For example, Wilson loops are like that. So this is a way of talking about symmetries that might act on, say, Wilson loops or 't Hooft loops rather than on point particles. That's one thing. So you get a notion of symmetry which can now apply to extended objects directly. That's nice and has led to all sorts of interesting developments. But another thing is that topological operators, they're fairly abstract objects. And to work with them, what you need to be able to assume is that they satisfy some kind of fusion rule. So if you bring two of them on top of each other, something should happen. So everything is topological. So whatever happens, you still have to get something topological at the end. And the idea is that when you bring together two topological operators, you should get some other topological operator. And this is an example of the kind of thing that could happen. So you could have a sum of topological operators appear when you bring together two of them. So as long as these things have some consistent action on the appropriate extended objects in the theory, it's fine. But if you take this perspective, it's actually kind of wild because it immediately says that the existence of these topological operators could be associated with symmetries that are not associated with symmetry groups. Because if you think about it, if you think of one of these operators, like one of these U's, as the generator of a transformation which is part of some kind of symmetry group, then if you compose two transformations that are supposed to be part of a symmetry group, you should get another transformation, a unique one, which is also in the group. But if you have multiple terms on this side, then immediately you cannot fit this into any kind of group structure. So this tells you that these are some kind of weird symmetries that are not going to be groups, which immediately takes us out of the realm of textbooks. So there's some kind of categorical symmetry. So whatever this is, it's not group-like. In the cases that are best understood, there's some kind of category theoretic structure. This is a reason why this modern perspective is useful. It's very abstract, but it lets us discuss symmetries and hence constraints on the dynamics of quantum field theory that go way beyond anything that we could deduce just by staring at the Lagrangian and looking for transformations of the fields. So that's a reason to take all of that seriously. Okay. But what I'm going to do in this talk is I'm going to try to focus on something that's much, much simpler than the thing that I just said. I want to focus on 1+1 dimensional quantum field theories, basically because they're relatively simple. You can draw pictures of everything that's happening, and there are some fun connections to various developments in recent literature. And in that context, what I'll be talking about is called the one-form symmetry. So a one-form symmetry is a symmetry that acts on Wilson loops. So a Wilson loop is a line operator in a gauge theory. It represents the insertion of for example, a heavy test quark or heavy test charge that you drag around some loop. And if you integrate out that charged particle, what you get left with is a Wilson loop.
Can I just ask a question?
Of course.
Can you go back one slide?
Yes.
Okay, so if you look at that fusion rule,
Yes.
these p-dimensional operators, then I thought that Gaiotto and company had deduced by deformation that for higher p, larger p, the things had to commute, which would mean some.
Well, so very good. So they did deduce that, but it doesn't mean, so I and j might, you might be able to commute I and j, but you might still get multiple terms on one side.
Yeah, you might, yeah, but that's a constraint number.
That's right. So in the paper from 2014, they actually did not consider the generalization I just discussed. What they focused on were group-like higher form symmetries.
Yeah.
What was realized later is actually the same formalism they introduced could be further generalized to consider non-group-like symmetries.
Mhm.
Sometimes they're called categorical symmetries.
Sure.
Other times you call them non-invertible symmetries, because basically, as soon as you have some pair of operators which you confuse and you get multiple terms on one side, it immediately means that some operators don't have an inverse, and some generators of the symmetry don't have an inverse, which it means it's not a group.
Yeah,
for example.
but I mean, there's a couple of points there. In both cases, whether you're considering this fusion structure or the formalism in their paper, you don't need a Lagrangian. Right?
That's right.
Yeah,
that's right.
So that's good. But on the other hand, if you have a symmetry group, you often are told, well, you act on the Lagrangian, you see what happens. But here, it's not just that you don't have a symmetry group, because if it's a symmetry group, you have to find out what it's acting on and so show it's invariant. This is just not a group.
That's right.
You don't need to even have the word symmetry there.
Well,
it's some kind of operation.
It's a question of definition. So certainly the conventional definition of the word symmetry would exclude anything like this. But the suggestion in the recent literature is you should define symmetry as the existence of topological operators that satisfy some set of axioms, which could be as general as.
Yeah, but supposing. Yeah, but Aleksey, supposing you had ui uj equals uk, right?
Yeah.
So then you say, oh, it's some sort of binary operation. There's some sort of group here. I have to check for the existence of inverses or whatever, right?
That's right.
But then somebody would say, is it a symmetry group? So then you'd have to think, what does it act on? I can only answer that.
Oh, absolutely, absolutely.
What's invariant, if anything.
That's right. That's right. Oh, I'm sorry. I think what I probably should have done on the slide is I should have also very explicitly indicated that it's important that not only do these things have a fusion rule with themselves, but that they have some action on charged operators that is consistent with that fusion rule.
Yeah.
I'll give an example of that in just a second, actually, in a much simpler case. Otherwise, it's empty. You're absolutely right. They need to act on something. Otherwise, it's not a useful thing. It needs to have an action on something in the theory. And hopefully that something is interesting so that you can deduce consequences about things you care about. Yeah, that's right. I won't talk much about, or maybe at all, about non-invertible symmetries in this talk. In the talk later today, probably I will, but not this one. Today, I want to focus on something simpler, which already is kind of fun. So 1 + 1D quantum field theory with a one-form symmetry, so it acts on Wilson loops. And from the formalism I just told you about, that would be if you plug D is 2, P is 1. Actually, you get 0. So you get 0-dimensional topological operators, which is just a local operator that generates the symmetry. So a one-form symmetry, saying a quantum field theory has a one-form symmetry, just means that it has local topological operators, which are just local operators that are topological. I'll explain what I mean by that in just a second. But they, like I said, they act on Wilson loops. And as soon as you say that, it means that there are lots and lots of models where you have such symmetry. So for example, there is two-dimensional SUN Yang-Mills theory. There is two-dimensional adjoint QCD with gauge group SUN. There is the two-dimensional QED with, let's say, fermions with charge n or scalars with charge n. Although I'll focus on the example with fermions because that's a kind of a classic example.
The difference here is just you've factored by the center. Why did you write the word adjoint there?
Oh, what I mean by that is if you have 2D SUN
different representation. Yeah, okay.
So basically, you could have just pure gauge theory, which in 2D is a bit trivial, but not completely trivial. Or you could add matter fields in various representations. So if the representation is adjoint, then you preserve what in the old literature would have been called center symmetry, and in new language would be called the one-form symmetry.
Yeah, okay.
Yeah, so that means you have lots of examples that are interesting in the sense that there are like hundreds of papers written about them already, and with this modern language, you might be able to say a bit more. Okay. So here I want to quickly state what the rules of the game are going to be for me. So I'm going to focus on basically the simplest kind of one-form symmetry, which is a Zeon one-form symmetry. It's based on the group Zeon. So the idea is going to be that if I have a Wilson loop and I have one of my generators of that one-form symmetry group, which is a local operator, so it's at a point right there. If I compare a correlation function where that local operator is inside the Wilson loop to one where I've dragged it outside, they differ by a phase, which is a Zeon valued phase. And also, if you fuse two of the basic generators of the group with each other, then you get another one. And if you take the nth power, you just get the unit operator. Okay. So here my fusion rules are super simple. So that's the kind of thing I'm going to focus on. And here there's all sorts of funny things that you can deduce. So first, one can show, and it will become a little bit clearer as I go why this is true, but one can show that the expectation values of these local operators are very tightly constrained. They can only be basically roots of unity, nth roots of unity. Okay, that's the only thing that could possibly happen. And if you look at the one which generates the Zeon group, so the thing I'm calling U1 of X, this is what it could be, and K is an integer here, and it is not yet fixed. Okay, it could be anything, and N is this capital N should be the same as this little n. That was a typo. So when you calculate this excitation value, you could get some random value of K. And that value of K is actually important. It has a physical meaning that I'm about to explain. K labels sectors within the quantum field theory, which have the possibly alarming name universes, for which you should blame Simeon Hellerman and Eric Sharp and a few other people who invented it, but it's been used more recently as well. So these are sectors of the quantum field theory, which have a very simple physical meaning. If you have a 1+1 dimensional quantum field theory, then you could always put a Wilson loop somewhere in it, some closed Wilson loop. And in 1+1 dimensions, the inside of a Wilson loop and the outside of a Wilson loop are well-defined things. So to get from one to the other, you have to go through the Wilson loop. You can't go around because you're only in 2 dimensions. So for example, here's a picture. Okay, so I have a Wilson loop and it has an outside and it has an inside. And to get between them, you actually have to go through the loop. So now if you calculate the expectation value of one of the local topological operators outside the Wilson loop and inside the Wilson loop, they are related by a Zeon phase, those two expectation values, which is the only thing that could be happening, which is consistent with these kinds of rules. Okay. But what it means is that there's an expectation value of a local operator which jumps when you cross Wilson loops. And in the literature, people refer to the sectors of the theory that you get by putting down Wilson loops, closed Wilson loops, as universes. And you might say that there's some kind of weird vacuum of the theory, but it's a bit subtle because in the theories that I'm considering, Wilson loops are probes of the theory. I don't have fundamental quarks, fundamental position quarks. I don't have charge one dynamical matter fields. So I could put a Wilson loop in that representation in the theory, but there's no excitation like that, which is dynamical in the theory. So what it means is that if you think of the Wilson loop as some kind of domain wall separating these two regions of the theory, that domain wall has infinite tension. It's a very heavy excitation, so infinitely heavy in the limit where I really have this symmetry as a bona fide thing. So one way to think about this is that if this operator is really topological, then its expectation value can't possibly change smoothly. It cannot have any smoothly varying dependence on x, for example. So at the most that could happen is you could have abrupt jumps, discrete jumps in the expectation value. Okay. So very good. So from here, we can actually quickly see a connection to confinement. Let's think about what happens if I have a big Wilson loop surrounded by nothing else outside. If I have a really big Wilson loop, then deep inside the Wilson loop, putting the Wilson loop into the theory maybe excites the theory right in the neighborhood of the Wilson loop. But if I go deep inside, then I settle into whatever the vacuum is inside. And then I can compare the vacuum energy density inside to the vacuum energy density outside the Wilson loop. And if the vacuum energy density inside the loop is bigger than it is outside, and the theory wants to minimize its energy, then what it would want to do is to shrink the Wilson loop if it could. And if you think what that means, it turns out you can argue that the expectation value of a Wilson loop in that situation is proportional to the exponential of its area with some coefficient, which is the tension, what's called the string tension. So if the vacuum energy inside is bigger than outside, then you get confinement of the test charges, which are represented by this Wilson loop. And if the tensions are exactly equal, which could happen, if the vacuum energy, I misspoke, if the vacuum energy densities inside of Wilson loop and outside are exactly equal, then you don't pay any area cost for changing the size of the loop. You only pay at most some perimeter cost. And that would be a situation where the theory is deconfined. Any questions so far?
Sorry, your previous slide, it looks very much like a topological charge or a charge that you can move inside or outside.
Yes.
Presumably these are, there's a description of these in terms of vortices. Is that what you would give?
Sort of. I'll show you very explicit descriptions of what these things, these weird topological operators look like in terms of fields soon. So for the moment, they're very abstract objects.
You mentioned that you could get an integer, an arbitrary integer randomly in this setting, but presumably it's selected.
Yeah, it's selected. So it's not completely random. So basically, which integer you get depends on whether what charge you have. So how do I put this? So if you have one, okay, let's say k is 0 for the sake of argument. So you found some region in space where k is 0. Then if you if in a neighboring region it's that integer was 1, the same integer was 1, then you'd be in this situation. And then you could say, aha, that means that what's happening is that to go from one region to the next, there was a Wilson line with the appropriate charge. So now you could say, okay, what if I only have a Wilson line at infinity? So maybe I don't have different domains in my theory, or maybe I just have like everywhere in space I have just one integer. What does that mean? What is controlling that integer? The answer is it's the charge at infinity in a sense. You could always take a Wilson loop and make it infinitely large, send it off to infinity, and depending on the representation of that Wilson loop, you will change the effective value of this integer k.
And one other question is just the Wilson loop. Normally, the way I would tend to use it is I would use it as a probe.
That's right.
I am not putting in a self energy for it or some contribution to the action. I'm using it as an observable probe. which means that in some sense, irrespective of whether the Wilson loop is there or not, if there is this charge inside that loop, the vortices must be present and not disturbed by that loop. Something, that topological entity must be there.
Yeah, so
I can see this happening in more detail in lattice models.
yeah, so well, think of it this way. Forget the topological operators for just a second. Let's imagine we never heard about them. It's still the case that if I take a 1 + 1 dimensional quantum field theory and I put a Wilson loop in it, generally speaking, there's a cost to changing the size of the Wilson loop. So the expectation value of the Wilson loop is not trivial. It's not a trivial quantity, and you could get into the situation, which is the one that I have on this slide, where the expectation value of the Wilson loop, you have area law expectation value.
Sure.
It's very common. Now the question is why? Like what is going on physically to cause that? And one way to think about what's happening is that the energy density of whatever is inside the Wilson loop is larger than outside. And that would actually drive that. So you can see this happening very explicitly in solvable examples, like in abelian Higgs models, for example.
Yeah.
Now, the dynamical mechanism by which all of this happens, just as you said, depending on the solvability of the example, but in some solvable cases, it really does come from proliferation of some vortices, potentially. Okay, like it's the quote unquote reason why you get different energy densities. So I would agree with that.
Okay.
But we don't have to specify the microscopic mechanism necessarily to discuss that phenomenon just yet. Right.
So that's still just the conventional point of view on Wilson loops, because you told us to forget about the topological operators.
That's right. That's right. And now I'm saying good. And so that was the conventional perspective. And now the only new thing is to say that actually there is a local operator. The Wilson loop is a line operator, but there's also a local operator whose expectation value jumps as you go from outside the Wilson loop to inside the Wilson loop. And that's this local topological operator, which is the generator of the one-form symmetry, or in the old languages we call the center symmetry. So, okay. So that actually is a natural segue to the next thing. So let's take some quantum field theory in 2 dimensions, 2 space-time dimensions, with a Zeon one-form symmetry. As I just tried to argue, what that means is that it has a bunch of interesting local operators that are topological. So they have some of the properties I just mentioned. Also, if you put 2 of them into the theory, separated from each other, you can move them around however you like. And the correlation function won't care unless one of them crosses a Wilson loop that you've also added somewhere else. So only like the linking number of these things with Wilson loops matters, nothing else. So that's the sense in which they're topological. But they're also just standard, apart from that weird feature that they're topological, so their correlation functions are like really constrained. Apart from that, they're just local operators. So you could always just add them to the Lagrangian. You can always add a local operator to the Lagrangian and see what happens. And that defines a deformation of the theory, like on the first slide of this talk. Of course, the next question is, what kind of deformation? Is it an interesting deformation? Is it relevant or is it irrelevant? So for this, we need to figure out this delta, the scaling dimension of the deformation by a local topological operator. And there's a pretty quick argument that tells you the delta is 0. Let's suppose that we work in the neighborhood of a, say, ultraviolet fixed point, as we usually do when we talk about Lagrangians. And consider, for example, this correlation function. So I have 2 of these operators separated by some distance. That distance is assumed to be small, so that I'm near a UV fixed point. I can calculate basically what I can think about what's happening in terms of that fixed point. And now I apply a scale transformation, and I get the following expression, where delta, which is as yet undetermined, is the scaling dimension of one of these operators. But now they're topological. So lambda inverse times x is just some other x prime, right? It's essentially moving around the point x. But using the topological property of these operators, I can just move it back to where it used to be for free. And then I get this relation. And to solve this relation, the only consistent solution is that delta is 0. So this deformation is maximally relevant. It's as relevant as something can be without like obliterating things like unitarity. So yeah, they're relevant operators.
Well, what about if you had more than one?
Oh, then you have multiple relevant operators. Sorry, you have multiple dimension 0 relevant operators.
No, but then when you try to make the deformation, you might bump into the other one.
Absolutely.
And cross.
Good. But you could bump into the other one, but nothing bad happens. So the only thing which is interesting that could happen is you might bump into a Wilson loop. If you put a Wilson loop somewhere, then it's more subtle. Okay, but Wilson loops are only probes of the theory, so they're not dynamical for me. So that never happens. But if I have two of them and they bump into each other, I'm talking about a Zeon symmetry. So the only thing that could happen is you could choose to think about two of them touching as some other third thing, but I don't have to. I could just think of them as two things touching it. There's nothing wrong with that. It's a consistent way of thinking about it. So, yeah, very good. So I have as many parameters that I can introduce this way as I have local topological operators. Now, a first reaction to this might be that this is skating right on the edge of being really boring, because we've all heard of one super famous dimension 0 deformation before, and that's the cosmological constant. Of course, it's only boring within quantum field theory. It's extremely interesting in the context of GR and cosmology. But in the context of QFT, it's boring because it doesn't do anything if you don't have gravity. But it does have scaling dimension 0, much like deformations I'm talking about now. However, the deformations I'm talking about now actually do stuff to quantum field theory in the absence of gravity. So for example, they can drive the theory through phase transitions, something the cosmological constant without gravity can't possibly do. So these operators are not trivial. These deformations are not trivial. They actually do stuff in the quantum field theory. So what I'd like to do now is to just focus on a concrete example where I can write formulas where there's a Lagrangian, there are fields, and everything is a little bit more familiar than it was before. Well, at least it might be, depending on what you've seen previously. So the example I want to focus on is two-dimensional quantum electrodynamics. So for me, that is U1 gauge theory with some charged Dirac fermions. And I want to make the charge n. Okay, it could be charge 1, but for me, it's going to be n. And to make that meaningful, I'm going to assume that the flux of the U1 gauge field on any closed manifold is quantized in some appropriate way. And if I assume that, then n is a meaningful parameter of the theory. And this is just what is in the literature called the charge n Schwinger model. Schwinger originally considered the n equals 1 version of this model. But in recent literature, people have suddenly started thinking about what happens if n is greater than 1. And there are some interesting new features. In particular, this is a famous and well-explored playground in which you could ask things that we'd love to be able to ask and then answer in real QCD, for example, in 4 dimensions, like do the minimal charge probes of the theory, in this case, charge 1, feel a linear potential if you separate them by large distance? Can you calculate the string tension if they do? And in this case, you can answer this kind of question. You can actually calculate string tensions and some limits. That's why people have studied it quite a lot, even though it's only in 2 dimensions. But the dream is that it gives us a little bit of insight into what confinement is like in other situations. So now this model is known to have a Zeon 1 form symmetry. And so it has local topological operators. This is true provided that the matter has a charge n. It wouldn't be true if the matter had charge 1. Okay. And in fact, this n is immediately correlated. So these n's are really the same. And these local topological operators, they have a few different descriptions. You could describe them in various ways. So one way to describe them is a little bit abstract. It's to say that these local topological operators are some kind of weird flux insertion operators. One way to think about that is that it amounts to taking the two-form field strength and shifting it by a delta function, which is localized at a point. So that inserts some flux. And if you think about what that would do inside of a Wilson loop, as compared to doing it outside of a Wilson loop, it would just shift the expectation value of that Wilson loop by some phase. That's probably stated too quickly. It's probably hard to follow that. But I will give a different description of these operators in a second, which is hopefully a little bit easier to digest. But that's one perspective, although rather abstract, and involves suddenly invoking some weird delta functions. It may seem a bit unfriendly. Now, to give you what I think is a somewhat friendlier version of expressions for these local topological operators, I want to switch descriptions. So this is the model as you normally first encounter it. It has a gauge field, it has a fermion that's coupled to the gauge field. But there's an equivalent bosonic theory that is obtained by two-dimensional bosonization from the previous thing, which involves the same gauge field, a compact scalar field phi, which is still coupled to the gauge field. And here I've switched to form notation, and I hope that some of you know it. And if you don't, the details of exactly how it works won't matter so much for what I'm doing. The mass term that I had over there, m psi bar psi, becomes m basically cosine of phi, although there's also a renormalization scale mu that enters the game for some subtle reasons that I'd rather not get into unless somebody really wants me to. But this has been also known since the time of Schringer, and well, I think it was certainly by the 70s with Coleman, people knew this very well. The one reason that it's nice to switch to this bosonic description of the theory, which you could do in 2 dimensions, is first, if you want to understand what's going on with like the string tension in the theory, this bosonic description is much easier than the original fermionic one. That's one thing. So as a result, it's used very heavily in literature. But a second thing is that in this bosonic description, it's way easier to write in a simple looking expression for these magical topological operators that I keep talking about. So actually, a first attempt at doing this could be along the following lines, which almost works but doesn't quite. So remember I told you that one way to think about these local topological operators is as a flux insertion. So you shift dA by this thing. And then you look at this action, and well, there's a prominent copy of dA floating around right there. So if you do that shift, whoops, and you forget about this first term just for a second, which I have to come back to because that's actually wrong. You can't forget about it. But if you forget about it just one moment and do this shift, then you see that doing the shift is equivalent to inserting an operator of this form. So just coming from basically from this coupling. So this term comes from here, and then naively you get another contribution from there because you actually do have to take it into account. And yeah, it looks like this shift, this flux insertion, is equivalent to inserting this expression into the path integral. And now everything here is just a field. So phi is the compact scalar, which is dual to the fermion. The gauge field is still the gauge field. The Hodge star got involved because this is supposed to be a local operator, so everything up here has to be a local operator, and dA is a 2 form. So I got to take the Hodge star of it to get a 0 form, also known as a local operator. This unfortunately doesn't quite work. So there is some good news here. So the good news is that this is a topological operator. One way to see that is that d of the derivative of the stuff inside here is actually exactly 0 by the equations of motion. One of the equations of motion is actually that. So that means that this thing is basically locally constant. That's a way of saying that it's topological. The bad news is the fusion rules that I advertised earlier imply that, for example, if there's no charge at infinity, the expectation value of the operator better be 1. But if you actually try to calculate it, it's not 1. It's actually UV sensitive and divergent. And it makes no sense. So it's not quite right. Now, you could try to absorb this funny UV divergence in the definition of the operator, and then you get the expectation value of that operator in the situation where there's no charge at infinity. But then, unfortunately, the change you need to make to define this thing messes up the fusion rules. So you don't get the fusion rule that you wanted. So it just doesn't work. And there's also other issues. So there's a better way of writing these local topological operators that actually works and gives them all the properties that they better have to be the generators of this one-form symmetry. But to do it, it is slightly awkward. Okay, so the thing that you can do is the following: you can linearize the action in terms of A. So you can make sure that the action is just linear in A, at the cost of integrating in some Lagrange multiplier field B. So, or some Hubbard-Stojanovic field. Sorry, I should have called it Hubbard-Stojanovic field B. So here there's a new field B, which appears in a few different places. So there and there. And if I integrate it out, I'll reach back to this action. But I could also just keep it around. And now I could ask, what does the flux insertion prescription for putting in one of these local topological operators do? And now dA is only appearing in one place, just there. And doing that flux insertion is equivalent to inserting this operator, which is now a local looking operator, which depends on this field B. And this thing actually has all the expected properties. It has the right fusion rules with itself. It has the right behavior when you cross it through Wilson loops. Its expectation values do everything that you would think that they should do that I advertised earlier. So this is an expression for the local topological operator in the charge and Schwinger model in terms of the fields. So it's a local operator. It's not one that people in the historical literature ever wrote down, as far as I could tell, but they could have. And it has scaling dimension 0 by the argument that I gave earlier, which was abstract, but it applies here. So nothing stops me from just adding it to the action. So I take the 60s vintage Schwinger model, upgraded slightly to make the ferment have charge n, and then I add this operator with some coefficient to the thing. And I actually have multiple operators like this, depending on the integer little n. And so I have multiple parameters in the theory. Okay. So here there's something funny happening that I need to highlight. When the fermion in the Schwinger model is massless, there is a Zeon chiral symmetry in the model. So for example, that chiral symmetry takes psi bar left, psi right, and multiplies it by a Zeon phase. So that's a chiral symmetry. In the bosonic theory, the thing which is dual to psi bar left, psi right is e to the I phi, and chiral symmetry multiplies that by a phase. So it acts like a shift on phi. Now, if you stare at this expression for the local topological operator, notice that it contains a phi. Also, the coefficient of phi has an n up here, but also an n downstairs there, so the n's cancel. So if I do a chiral transformation, which is a shift of phi, which would have this effect, I necessarily get a transformation of the local topological operator. I can't escape that. Now, this is only particularly interesting if I actually have chiral symmetry. This is a symmetry of the model, which is only true when the fermion mass is set to 0. But that is a valid point to ask about, valid point in the primary space to discuss. And the fact that a generator of a one-form symmetry is charged under some other symmetry is actually a signal of a mixed 't Hooft anomaly. So there's a mixed 't Hooft anomaly between the Zeon chiral symmetry and the Zeon one-form symmetry. And it also means that if I add this operator to the action, oops, like I did here, and I do it when I have a chiral symmetry, so the quark mass is 0, fermion mass is 0, then adding these operators breaks chiral symmetry. Now, if I have chiral symmetry, then maybe I don't want to add them. But if I don't have it in the first place, nothing stops me from adding these things.
But, sorry, am I missing something? Or if I just replace, if I go back up your arrows and I put in upside bar up psi instead of this phi, what you've added is a mass term. So your chiral symmetry.
It's sort of, but not quite. So basically, if you look at this thing here and I factor out the phi bit, and it looks like e to the I phi times some other stuff. You could say that e to the I phi is a mass term, but the thing that multiplies it is still non-trivial. So it's not quite a mass term by
It's
itself.
not quite, yes, I agree. But
it's like something times a mass term, but that something
yes,
is field dependent.
But there's a mass parameter associated with, so the chiral symmetry looks like it would be broken by
exactly. So from that point of view, it's very natural to say that this breaks chiral symmetry, but that's true. It breaks chiral symmetry. Yes, it's charged under chiral symmetry. But what's funny is it's also a generator. This operator is a generator of another symmetry. So it's like the generator of one symmetry is charged under the other one. In this modern language of topological operators, that is like the way that anomalies appear, actually.
Sure, but
it's very
just to clarify a little bit more, if I put it back into the original Schwinger model, do you know what it would look like? I mean, that B term is that I have to integrate out.
Yeah,
looks like it might make it non-local.
No, it's basically it's like the exponential of some number times epsilon mu nu f mu nu. So B, by the equations of motion, basically B is related to star dA. So star dA for me is just epsilon mu nu f mu nu.
The equations of motion won't be affected by adding this to the action. They look like they should be.
Well, the equations of motion for A are not.
Oh, for A, okay, all right, yeah.
But the equations of motion for B certainly are affected. So, I mean, this thing does change. So adding this really does change the theory. It doesn't change that it's a topological operator, but it does change the theory. So it's really not a mass term. I want to emphasize that. But its charge is the same as the charge of a mass term. So to say it another way, once you realize this stuff is there, what you've just discovered is that there are multiple relevant there's more than one relevant operator which acts like a mass term in terms of its symmetry properties. That's kind of startling. Okay, if you'd asked me before I started this project whether that's there, I would have said, of course not. It's just a mass term. But there's actually this other thing. So now what I want to try to explain is what is the effect of all this? Like you could do this, you could add it. Okay, so well, let's discuss it in the simplest possible case, which is still non-trivial, however. And for that, I want to take n of 2. If I take n to be 1, then everything trivializes and I don't have anything interesting to say. But let's take n of 2. Well, then I could integrate out both A and B. So I have my gauge field, I have this funny auxiliary field B, and I also have the scalar field phi, which is dual to the fermion. And I could integrate out the gauge field and the auxiliary field B. And I leave alone phi. And then I get an effective action, which just depends on phi. And you might say, okay, easy to say, hard to do, because how can you possibly integrate out so many fields? But the Schwinger model in its bosonized description is very special in that you can do that, because the action is quadratic on A and it's quadratic on B. And you could actually do it if you do it in the right order. You could integrate out the fields, and you get a closed form expression for an exact expression for the effective action. And basically, the effective potential for phi, the remaining field, looks like this. So let's, for the moment, forget the red term. I want to explain what happens if there's no red term. The red term is the effect of the deformation. But let's say there's no deformation. Then it would be very standard. People did it like before I was born. Schwinger did it. Okay, so that's the first term. So you get basically a phi squared term for the scalar field, with the coefficient, which is, oh, there's a typo. There should be a squared there. There's a 2 missing in an exponent. This 2 is there because that's actually n. The 2 pi downstairs is just 2 pi, but the 2 up top is really n, and there's a squared missing. And I'm being careful here with integrating out the gauge field. That's what gives me this funny shift by k. I'm happy to explain that if somebody wants, but if you want, for the moment, just imagine k is 0. Okay, it's a possible value for k, although it doesn't have to be 0. So if k is 0, then if you forget the second 2 terms, this is just phi squared with a coefficient, which is e squared. So this is saying that the scalar field phi picks up a mass, which is proportional to the gauge couplet. That's what Schwinger showed like in the 60s. If you add a mass term, then you get this wiggly potential for the scalar field as well. And if you add the deformation that I've been talking about by these local topological operators, you also get this funny shift, which is proportional to my deformation parameter lambda and another cosine. And now this integer k comes back in. Okay, so actually k controls which universe am I in. So basically I have to, like, to talk about the effective potential, I have to decide what is the expectation value of my basic topological operator. Is it 1? Is it, e to the 2 pi I over n? Is it e to the 2 pi I times 2 over n, or whatever? This is a question of what's my charge at infinity. Depending on the charge at infinity, the effective potential for the scalar field is different.
Wouldn't it be most natural? Sorry, wouldn't it be more? Wouldn't one expect to have the sum over k?
Yes, absolutely. So in the full path integral, there's a sum over k, and so the path integral decomposes into like something with like a sum over different values of k, and for each k there's an effective phi which experiences the potential described by vk. Nice if I could write something, but it's not easy for me.
That's okay, but I expect that it's unnatural to select the k. That if I was to simulate the thing by putting the model it on a computer, nothing would pick out k.
You're right. You have to sum over k.
I would fluctuate. Okay. All right.
You have to sum. K is summed over. The full partition function contains a sum over k, but you can write the partition function as
sure. No, I appreciate that. That's sure.
And I'm just trying to describe like what the potential that phi feels in each of these pieces looks like, because it turns out that way of thinking about it has some interesting consequences for confinement. But you have to sum over k. Yeah, in the end, you cannot fail to sum over. So what's important in this expression is that dialing this deformation parameter affects the relative vacuum energies that the field phi feels. So the vacuum energy is completely uninteresting. Like it's the same for everybody. But here, depending on k, you get a different kick to the vacuum energy. So the differences in the vacuum energies between different k's, that matters. So let's think about these effective, this potential, okay, for as a function of phi in the charge to Schwinger model with various values of the parameters. So for example, here's what it looks like if you set the mass to 0, the mass term to 0, and you turn off the deformation entirely. Well, you could look back at this expression, you throw out this term, you throw out that term, you just have a quadratic thing. But phi is a periodic field. So there's some identifications in field space, and so you basically get 2 branches in the effective potential. And phi could have, the minimal value of the, how do I put this? The equilibrium value of phi could be there or there. So either phi wants to be pi or it wants to be 0. And 0 is the same thing as 2 pi. So if phi wants to be pi, then e to the I phi is -1. And otherwise it's 1. So, and remember that e to the I phi is basically the same thing as psi bar psi. So it's the chiral condensate. So this would mean that there are 2 degenerate chiral vacua. So there's a spontaneously broken Z2 chiral symmetry. But there is also a spontaneously broken Z2 form symmetry, because as you go from one chiral vacuum to the other, the expectation value of the local topological operators jumps. And the 2 chiral vacua, if you have domains where you have one chiral vacuum over here, another one over there, the thing that separates them is actually a Wilson line. The fact that Wilson lines do something to chiral symmetry is an imprint of the 't Hooft anomaly between the one-form symmetry, which acts on Wilson lines, and the chiral symmetry, which acts on psi bar psi. The 2 symmetries are tied together by the anomaly. If you turn on the deformation but keep the mass turned off, the effect is to shift the vacuum energy. So you shift the 2 curves relative to each other. The fact that these 2 minima are now non-degenerate means that you've explicitly broken chiral symmetry. And the fact that the vacuum energies of the 2 points are different also means that, for example, here the vacuum energy is higher than it is there. And so if you have a region where the chiral condensate is -1 in appropriate units, that means it's surrounded by a Wilson loop. And the theory would want to shrink that region to nothing, if it could, to minimize its vacuum energy. So that means that the Wilson loop would want to shrink, and its expectation value would be area law. So that would be a signal that the theory is actually confining in the situation. But notice that you can get into this in this particular situation by dialing the coefficient of deformation while leaving alone everything else. And then you could change things around. You could turn on the mass term without the deformation. The picture looks similar, but with a few differences. And now you also explicitly break chiral symmetry, and you have confinement. Or you could tune the 2 coefficients against each other, and then you have explicitly broken chiral symmetry, but you might get into a situation where you have a exact degeneracy between the vacuum energy here and there, and that would signal spontaneously broken Z2 form symmetry. I want to say that the reason that you have explicitly broken chiral symmetry here is because the curvatures of the potentials around their minima are different. The vacuum energies are the same, but the vacua are inequivalent now, in any sense. The curvatures are just different. So what that means is that the phase diagram for the Schwinger model has an extra parameter relative to what people in the old days thought. So it has a parameter, which is the quark mass, fermion mass divided by the gauge coupling. That one people knew about. There's also a theta parameter. Let me not talk about the theta parameter. It doesn't add anything interesting to what I'm saying. I'm gonna forget it. But there's another parameter, which is this coefficient of deformation by the local topological operator divided by the gauge coupling squared. And if I draw a phase diagram, I have a big confining region on one side, another confining region on the other, and there is a curve which starts there and just keeps going, where the theory is deconfined. Okay, so along the red curve, the theory is deconfined, and then away from that line, the theory is confining. All of this is to say that the deformation has a profound effect on the physics of the model. It changes whether the thing confines or not. That's as profound, it's as dramatic as it can get. Okay. So now it's important for me to explain, like, why did I decide to call these deformations universal? In which sense are they universal? So one sense, their effects are exactly calculable in a completely model independent way. Like, I presented it to you as a discussion of what happens in the Schwinger model, but actually I didn't have to. There's a model independent way of explaining what they do, which doesn't require any calculations in any particular model. And also their only effect is on the vacuum energy of these universes. So the 2 senses, they're universal. So for example, to see what the effect of one of these deformations is, consider the path integral written here in some heuristic form. So I have an integral over the fields, some Boltzmann weight from the action, and then I have my deformation. And I can always expand the deformation formally in, like this. Okay, just Taylor expand this exponential. This is something you could always do, but it's often somewhat useless because, okay, you get a bunch of integrals of expectation values of various combinations of the deformation operators. Well, normally you don't know what all of those are, so it's not that useful. But here, because they're topological, you know what all of these expectation values actually are. So you can just use that and simplify what you get. The correlation function is just read off from the fusion rules. So you can actually do the sum in closed form, and you get the difference between the old partition function, which is undeformed, and the new partition function, which has the deformation. And the entire effect is to shift the vacuum energies. It's the one and only effect. It shifts the vacuum energies relative to each other. And as I've argued before, that controls what the theory confines or not. Okay, so I'm basically over time, so I should probably find a way to wrap up.
No, there's no rush like that, not from our point of view, so.
Okay, well, I'll still try to be reasonably organized. So let me try to highlight two quick consequences, relatively quick consequences that I think are amusing. So one is kind of a fun little lesson about confinement in 2 dimensions. And another is a counterexample to the effective field theory naturalness principle. So first, let's talk about confinement in 2D. So confinement is always a question about the behavior of large Wilson loops. At least in any context where we know exactly what we mean by confinement, what we mean is, what does a large Wilson loop want to do? Does it have area law or not? And in 2 dimensions, that's a question about a comparison of vacuum energies between the vacuum energy of the region inside a Wilson loop and outside. And as I've just argued, vacuum energies are sensitive to these universal deformations, and so confinement is as well. Okay. Now suppose your goal in life, you have some theory, okay, that you have some suspicion deconfines. Okay, maybe you did some calculation with it using some approximation, and you found some evidence, you think, that it's a deconfined theory. To really be sure that you're right, you need to prove that these local topological operator terms are not generated radiatively. Like, you might have not added them to the action, maybe you never heard of them before. But how do you know they're not generated radiatively? They're just some random local operators. They could be generated radiatively unless you can forbid them. Now, if they're charged under a standard symmetry, and that symmetry is a symmetry of undeformed action, then they won't be generated. That's a standard thing. But there are interesting examples like 2D, adjoint QCD with an odd number of colors n, where the local topological operators are actually just neutral under, say, chiral symmetry. So naively, nothing can forbid them from being generated. But nevertheless, there's some old evidence that going back to papers by David Gross and Igor Klebanov and many others from the 90s, that the model is deconfined. So then how? So the only convincing way that I know to argue for that old result actually is a very recent one. And it's due to the work of Komargodsky and others, which points out that this 2D adjoint QCD has some really exotic symmetry that is not at all visible at the Lagrangian level, which is non-invertible. And under that symmetry, the local topological operators that generate the one-form symmetry are charged. There's some non-Lagrangian symmetry that actually prevents these things from being generated radiatively. So that's one comment. Let me skip that. Okay. So let me just go to the punchline of this part of the talk, which is that unless you fine-tune your 2D QFT by adding these local topological operators to the action and carefully dialing their coefficients to drive yourself to a deconfining point, generically you'll get a confined theory. So confinement is actually the generic scenario in 1+1 dimensions. It's very robust. You have to do something very special to get deconfinement. You either need some very special 't Hooft anomaly or you need fine tuning. Okay, so that's one thing. Another thing is to do with the naturalness principle. So let me try to explain what I mean by the naturalness principle. So the naturalness principle is something like the following statement, that if all operators that are not forbidden by a symmetry of the infrared theory are generated by quantum fluctuations with some scale which is set by the scale of the operators that are breaking your symmetry. So to avoid this, you need to fine-tune new parameters. So a huge fraction of the modern particle physics literature is dedicated to either fighting or exploiting this principle. So people argue about this kind of thing a lot when they talk about the Higgs boson, about the cosmological constant, about the strong CP problem. People present it differently. So I don't know if you like the way I presented it, but the basic principle is all over the place in particle physics. So basically, that which is not forbidden is generated. That's another way of saying it. So in the examples that I'm talking about, there is a weird way in which this principle seems to be failing. So let's focus on the example that I've had, say in the Schringer model, where I have a one-form symmetry, the Zeon one-form symmetry, and the chiral symmetry, which is in the massless limit, is present, and they have an 't Hooft anomaly between them. So the local topological operators are charged under chiral symmetry. So if you add them to the action, they break chiral symmetry, and they're relevant deformation that breaks chiral symmetry. So you might think that if you add them to the action, you break chiral symmetry, you'll generate a mass term, because it has the same charge under chiral symmetry. So what would prevent you from generating a mass term? And yet you can add these weird topological operators to the action. You break chiral symmetry for sure, but you can calculate the effect of adding them exactly in closed form, and they do not generate a mass term. The theory does not generate a mass term. Like, for example, if it did, the spectrum of particle excitations around each vacuum in the theory would be affected, but it's not. The only thing that's affected are the relative vacuum energies. So despite the fact that if you turn on these local topological operators, you might think that a mass term could be generated. It simply is not. That, I think, is a failure of effective field theory naturalness, at least as it's commonly presented. So to say it another way, imagine that your one-form symmetry is itself not exact. It's broken at some very high scale M up here by the presence of some very heavy fundamental charged, minimally charged matter fields. Then, okay, above that scale, there's no one-form symmetry, but below that scale, there is an approximate one-form symmetry. And then, okay, you have some approximately topological operators you could add to your action with some coefficient lambda. And then very far below that scale, for example, you might have your gauge coupling, like in the Schringer model, which will tell you basically the mass scale of the meson excitations of the theory. And then, well, the chiral symmetry, there's no chiral symmetry in the model because you've added this term. And there's no one-form symmetry anymore either because I have the symmetry broken at some very high scale. So you must generate a mass term. But in the limit that you take this one-form symmetry breaking scale to infinity, the argument I just gave you means that the mass term scale has to be 0. So that means that there's an anomalously small mass scale in the theory, which is basically proportional to lambda over m, where lambda is the size of the deformation and m is the size of the scale of the dynamics that breaks the one-form symmetry explicitly. But to understand that in detail requires understanding emergent one-form symmetries a lot better than they're currently understood. So with the present technology for thinking about emergent one-form symmetries, it's very hard to do a concrete calculation to support this heuristic picture. And it has not been supported yet.
just the problem with that picture is that M should, to have any sensible order here, M, I would have expected, should be less than lambda, because lambda is more or less my cutoff of the theory. And to say the symmetry is being broken at a scale that's much higher than that, it seems dubious to me.
So good. So lambda here is not a UV cutoff. The UV cutoff is somewhere up here. So if you want the lattice that I'm using, 1 over A is somewhere up at the very top of the slide. Then I have some field, which is charge 1, which is light compared to the UV cutoff scale. But it's very heavy compared to, compared to other scales, for example. So compared to the scale of the physical gauge coupling.
So what is lambda meant to be?
Lambda here is the coefficient of the local topological operator.
Oh, sorry, yes, it's the coefficient of the local topological operator.
Yeah, sorry. So
yes,
indeed,
okay.
You're absolutely right that lambda is often used as UV cutoff, but that's not.
Sure, no, it was the difference between lambda and M.
N is the
seem
charge
like the same
of the
thing.
light field. N is the charge of the light field. M is the mass of a charge 1 field, which is assumed to be very heavy.
Sorry, M is the charge of it. So, or M is the mass of the one form. Now, M is supposed to be a mass scale, isn't it?
So, sorry, I think I'm not enunciating very well. I apologize. So N, this N, which I'm pointing to right.
Oh yeah,
here,
that's the charge. Yes, that's
N
fine.
is a charge of the light field.
Yes. No,
which is coupling to this.
But it's capital M and lambda that I'm confused with together. You've clarified what lambda is. So, what little m, what capital M is?
Capital M is the mass of a charge 1 field. So
okay.
So if I remove the charge 1 field, if it's infinitely heavy, then I only have a charge N field, and then I have my one-form symmetry, and it's exact.
Okay.
If I now bring in a charge 1 field, then I no longer have an exact one-form symmetry. In the QCD language, what you would say is, if I have fundamental quarks, I don't have a center symmetry. But if they're infinitely heavy, then I do. So, but if they're not infinitely heavy, they're just very heavy, then way below this, that mass scale of the mass of the very heavy quarks, I have an approximate center symmetry for many purposes. And in this 2D context, that means I have approximately topological operators which I can add to the action with a coefficient lambda or lambda squared as it happens. And then I can ask what happens. And now the question is there a mass term generated for the light fields, which have charge N? And if so, what is that? And symmetry would say, normal symmetry and effective field theory arguments would say, well, you've broken the symmetry at this scale. The symmetry would protect the mass of the charge N fields. So you might think that this M psi would be up here. And what I'm saying is it's not. It's actually very small. It has to be very small for consistency with everything else I've said. So that's surprising, at least to me. But what I would really love is to actually not just argue for this kind of diagram, but to do a computation that gives this diagram and basically tells me, well, okay, what exactly is the power of this parameter lambda over M? Is it 1, as I've said, or is it 2, or is it some fractional power? Like, I actually don't know, because I haven't done the calculation that gives this picture. I've just argued that it should be something like this. And the reason is that emergent one-form symmetries are not particularly well understood at the moment. So let me summarize and then stop, because I've already talked for too long. So what I've tried to convince you of is that there are interacting non-supersymmetric quantum field theories that have exactly solvable deformations. So there are parameters that these quantum field theories have whose effects can be understood exactly in closed form. And the magic that one needs for this is to have a D- one-form symmetry. And I was in 2 dimensions. So for me, Q was 2. So I was a one-form symmetry. And specifically in that context, there are some interesting implications for confinement of charges. And also some interesting violations of the effective field theory naturalness principle. I think there's a couple of sort of obvious next steps that should be pursued and that I've been thinking about, but I don't have any complete results to share. So one is to explore this naturalness violation further. It is a naturalness violation in a context where we don't necessarily care about naturalness that much, namely 2D quantum field theory. What we would really want is an example in 4D, especially an interesting one. I don't have one like that. However, violations of the effective field theory and naturalness principle are very, very rare. So any one that you stumble across should be studied carefully, just in case, because maybe it teaches us something about what we really want to know about, which is what happens in 4 dimensions. And the other thing is part and parcel with that. We need to understand emergent one-form symmetries a lot better than we currently do. So that's something that I'm working on very actively, both because I think it's interesting for its own reasons, and also because it might help understand this first point. So with that, I want to stop, and thank you so much for listening.
Well, thank you very much for a fascinating talk. Questions? Jasmine?
I was just wondering if this would have any applications in the near future to, like, say, the electro-weak phase transition.
I somewhat doubt that it would have applications in the near future along those lines, because that, like, the electro-weak phase transition is a statement about what the standard model of particle physics does, and that's a 4-dimensional model which actually doesn't have any simple one-form symmetries that I could point to, whereas I was focused on 2-dimensional models which do have one-form symmetry. So it'd be hard to use it for that.
Okay.
Mitad Unsel explained a little bit of his work on, I think it's called the Velen model, which looks,
That's right, yes.
which has a one-form symmetry.
Absolutely.
Is that you should be able to calculate in that setting, I would have thought. It has something close to your diagram.
So yes, his work on abelian gauge theories in the Velen formulation on the lattice was for 2 + 1 dimensional abelian gauge theories, I believe.
Yes, it was. Yes, yeah, that's.
And in that context, the generators of the one-form symmetry there are not local topological operators. They are topological line operators. They're supported on lines instead of points. And so you cannot add them to the action. You can only add local operators to the action, in a sense. So you cannot directly apply what I've been saying here to Mitad's work in 2 + 1 dimensions. Now, Mitad does have some other recent work, actually with the same people as that paper on the Velen formulation. So with Mendel and Yuya, on 1 + 1 dimensional Yang-Mills theory without matter. And that one does have local topological operators. Not only that, but the symmetry group, or sorry, I apologize, the symmetry of 1 + 1D Yang-Mills theory is not even Zeon. It's much bigger. It has non-invertible topological operators. Mm-hmm. So the symmetry group is huge. And you could add all of those to the action if you want and play around. And in the paper that we wrote, we actually did that with my students. But it's more complicated, so I didn't talk about it. And also 1 + 1D Yang-Mills is an almost topological theory, and so it's a bit less interesting because of that.
Area profound. Area preserving diffuse. Yeah.
It preserves area preserving diffeomorphisms are symmetry.
Very interesting. The other thing that struck me as you were speaking there was that your vacuum energy, you were able to access different signs for it, in principle.
That's right.
That's right. So is there something that I can add in 4 dimensions? I'd like to balance the cosmological constant in some way. Maybe.
Yeah, so in 4 dimensions, if you had a 3-form symmetry,
3-form, yes.
then you could play the game that I just discussed, and then you could try to, tune your deformation coefficient against the cosmological constant.
But a 3-form symmetry is dual to a 1-form symmetry, so.
Well, I think I know what you mean by that, but it's a bit 3-form symmetries, as far as I can tell. So they would act on like weird, like membrane-like objects.
Yes.
Instead of line operators.
Sure.
And they are, as far as I understand, they're somewhat less common than 1-form symmetries in 3 dimensions. So trying to think what I want to say about that. So I do know examples of 4-dimensional quantum field theories with 3-form symmetries, but they're somewhat contrived. You have to so for example, you could take QCD or Yang-Mills theory in 4 dimensions. And then there is a way of constraining the sum over instantons so that you exclude some topological charges without violating cluster decomposition, which is a bit surprising. But there are ways to do this, okay? And if you do in a consistent way, then the consequence is that you get a 3-form symmetry. It's a bit contrived, okay, because you could ask who ordered that, but you could do it. And it has some fun consequences. But I don't know of any example where some theory that somebody was already interested in for their own reasons already had a 3-form symmetry. That doesn't mean it doesn't exist. I don't know of that. But if we had one, then it would be fun because you could maybe try to play it off against the CC.
Yeah, excellent. Well, thank you very much. I'm going to stop the recording.
Okay. Well, thank you so much for the invitation to speak. It was great fun.